Hello students, welcome to another video. Today's topic is chemical equilibrium. First we know about equilibrium. So in case of equilibrium, there are two sides. This side is known as reactant and this side is known as product, and this is the sign of equilibrium. In case of equilibrium, in case of the forward reaction, when A plus B forms C plus D. Okay, then in case of the forward reaction, the concentration of reactant decreases. What happens here? The concentration of A and B decreases and the concentration of C and D, means the product, increases with the time. In the forward reaction, the concentration of reactant decreases and the concentration of product increases. In further, if we combine these two equations with time, the concentration, this is the graph of product and this is the graph of reactant. But the equilibrium is such a position in which the concentration of reactant is equal to the concentration of product, and this graph is known as equilibrium point. In this position, the RF means rate of forward reaction is equal to rate of backward reaction. What is the definition of equilibrium? Equilibrium is a condition in which concentration of reactant is equal to concentration of product. The equilibrium is such a condition in which the concentration of reactant, the concentration of A and B is equal to concentration of C and D. The concentration of reactant is equal to the concentration of product. So now the characteristics of equilibrium. It is dynamic in nature, but it shows both forward reaction and backward reaction. Rate of forward reaction is equal to rate of backward reaction. In case in the situation or condition of equilibrium, the rate of forward reaction is equal to the rate of backward reaction. So RF is equal to RB. Del G, change in Gibbs free energy or change in free energy, is equal to 0. Let A equilibrium be E, then let G1 is the for reactant G1 the Gibbs free energy and G2 for the product Gibbs free energy. Let's change G2 minus G1 is equal to 0. So del G is equal to 0. So there is no change in Gibbs free energy in case of equilibrium. Further, the entropy change del S is also equal to 0. The catalyst does not affect the equilibrium, it only alters the rate of reaction. If we use a catalyst in the equilibrium equation, then it can't affect the equilibrium. This can't affect the equilibrium position, but it can increase the rate of reactions, so that the reaction may take fast or the reaction may take slow, but the equilibrium will be held. It must be carried out in a closed vessel so that no outer or substances can affect this equilibrium position. Then law of mass action. What is the law of mass action? The rate of reaction is directly proportional to molar concentration of reactant at a given condition. What is mass action? The rate of reaction is directly proportional to molar concentration of reactant at a given condition. At a given condition, the molar concentration of reactant is directly the rate of reaction is directly proportional to molar concentration of reaction. Let's consider a equation. A is the molar concentration of A and small b is the molar concentration of B. But A plus B gives us product. The rate of reaction, according to the law, rate of reaction R is directly proportional to molar concentration, means concentration of A whole to the power A to concentration of B whole to the power B. So R, let we take an a rate constant known as K. So R is equal to K into A to the power A, B to the power B, where K is a rate constant or velocity constant. Let us consider an example. 2A plus 3B tends to product. Here small a is equal to 2 and small b is equal to 3. So R is equal to A to the power 2, B to the power 3. So R is equal to K, A to the power 2, B to the power 3. If we take n number of substances in the reactant side, then xx plus yy plus mm plus nn plus aa tends to zz. So r is equal to k into, and we have the rate constant k into what we have to do, concentration of this and to the power the molar concentration. Then k is equal to x to the power x, y to the power y, m to the power m, n to the power n, a to the power a, and so on. Then law of chemical equilibrium. Let us take an equation of a plus b equilibrium mm plus nn. All the substances are in the gaseous conditions. So this is rate of forward reaction and this is rate of backward reaction. The rate at which a and b react proportional to a to the power a, b to the power b. The rate of a and b directly proportional to a to the power a, b to the b. Rate of forward reaction rf, the constant is kf, a to the power a, b to the b. Similarly, the rate of, let first case we take the forward reaction. Then the rate constant for the forward reaction is called concentration to the power reactant. For the forward reaction, the reactant is this, so the RF is called kf, a to the power a, b to the power b. So for the backward reaction, the reactant side is this, so the rate of backward reaction is called RB, KB, m to the power m, n to the power n. As per rate law, we know RF is equal to RB. In previously, we found that RF is equal to KF, a to the power a, into V to the power B, and RB is equal to KB, m to the power n, n to the power n. So KF by KB, we divide KB to this, take KB to this side, then this term will divide in the right hand side. So kf by kb is equal to m to the power n, n to the power n by a to the power a, b to the power b. So k is equal to m to the power m, n to the power n by a to the power a, b to the power a. We take is the total equilibrium constant, rate of forward. Kf by kb is equal to k is equal to equilibrium constant, kf rate constant of a forward reaction, and kb is equal to rate constant of a backward reaction. This is all about today's. In the further video we will discuss about thermodynamic derivation of chemical equilibrium. So if you like video, then like our video and subscribe our channel. Thank you very much.